Hi everybody, we're going to finish up section 1-2 where we're looking at our linear equations and rational equations. And right now we're really going to focus on those equations that are rational. We've already looked at the basic cases of linear equations and how to solve those, and we said we need to do unto one side as we do unto the other. We need to keep our equations in balance, and we also said that we need to kick our order of operations in reverse, and we need to say, okay, if I knew what that variable was and I plugged that number in according to order of operations, what would I do? And then we're going to completely undo that in reverse order. In other words, we're going to undo what has been done to the variable in opposite order and kick our order of operations in reverse. But right now we're going to look at our linear equations with fractions, because remember, that's what rational means. Rational doesn't mean rational, dude. It means can be written as a fraction. Now, there are two methods for solving your linear equations, and what I'm going to do is I'm going to show you both methods, but know that you don't have to know both methods. I'm going to show you both. You decide the one that you like and you go with that method. I will also show you that one of these two methods later, much later in the semester when we start dealing with rational expressions, and recall, an expression does not have a what? Right, an expression does not have an equal sign. Right now we've got equations, and so we're going to have equal sign in here. But later when we have expressions and there's no equal sign, one of these methods you won't be able to use. I'll let you know which one, but for now just know that pick the one you like and go with that one. Now, I'm going to first give you an example, and then we'll come back and fill these in. So the example that I'm going to give you is, let's see here. We are going to solve x over 6 plus x over 8 equals 1. Now, what's going to happen here is that with our method 1, there we go. Okay, with method 1, what you do is you retain the idea that you have fractions and the fact that in this particular case, we're going to be adding those two fractions. So you need to ask yourself, what is it that I do when I add fractions? Remember, our gang symbol reminds us that when you multiply fractions, you cancel on the diagonals, cancel up and down, and then you shoot straight across. But we're not multiplying here, we're adding. So this is the case where you get a common denominator. So I'm going to get common denominators on these fractions. I'll look and I say, what's the smallest number both a 6 and an 8 will go into? 24. Yeah, so I'm going to take that 6 and that 8, and I'm going to turn each of those denominators into the common denominator of 24, the LCD of 24. And then what I'm going to do is I'm going to carry that LCD all the way across that equation. Now, we've discussed before that what happens is I'm going to take the 6 and multiply it by 4 to create that denominator of 24. Remember, that means that I also need to multiply my numerator by 4. Because remember, I don't want to change the value of this fraction, only what it looks like. A 4 over 4 is going to be a 1. So 4 over 4, when I multiply this fraction by 4 over 4, I'm really multiplying the fraction by 1. When you multiply by 1, do you change value? No, not at all. Anything times 1 is going to be itself. So I'm not going to change value here by multiplying the numerator by the same thing. So this becomes a 4x. And then on the other fraction with that 8, I'm going to multiply it by 3. That means multiply the numerator also by 3 so that I don't change the value of the fraction, only its looks. Because 3 over 3 is just a 1. Multiplying by 1 never changes value. Now, this other 1 over here, right here, I'm going to turn it into a denominator of 24, so that would be a 24 over 24. So I've taken the entire equation and I've converted it into a bunch of fractions. Now, when I'm adding fractions and I have these common denominators here, what I'm going to do next is I'm going to add up the numerators and keep the denominator. Remember, the denominator is the superhero of fractions. So I'm going to keep the denominator. I worked awfully hard to get it. I'm going to retain it, and I'm just going to add the numerators. So a 4x plus a 3x will give me a 7x. And on the other side, I've got a 24 over 24. What I have at this point is a proportion. And what this is saying is, remember our pan balance. Here's the fulcrum, here's the pan. So this is saying that this fraction is on this side of the pan, and this fraction is on this side of the pan. If the equation is balanced, and I've got the same thing in each pan, and that means that the two fractions are equal. If the fractions are equal and the denominators are the same, then what has got to be true about those numerators? What has to be true about this part up here? Yeah, they have to be the same. That's the only way those two fractions are going to be the same. If the denominator is the same, the numerators have got to be the same. In other words, if this 7x right here is not a 24, those two fractions are not going to be the same. So I'm left with 7x equals 24. That is a very simple equation to solve. You know what to do with that. You know to just go through and divide by 7. Now, always simplify your fractions if you can. Is there a number that will go into both 24 and 7? No, there isn't. Don't worry about turning it into a mixed number unless you're told to turn it into a mixed number. At the college level, we love improper fractions, so just keep it as an improper. So that is method 1. That means that in method 1, what I'm going to do is I'm going to keep the idea that I have fractions, and I'm going to get common denominators. I'm going to adjust the numerators. And then I'm going to combine the fractions by adding or subtracting. And when I do that, I will have a proportion, and all I need to do is solve the proportion. Fairly easy to do. And that's method 1. Now, what happens with method 2 is, method 2 says, I'm going to take these fractions, and I don't like fractions, so I'm going to completely wipe them out. So then, in method 2, I'm going to use that LCD again, but I'm going to use it in a different way. Like I said, method 2 says, I don't even like the fractions. I'm going to completely get rid of it. So I'm going to take the LCD, and instead, I'm going to multiply the entire equation by the LCD. And I mean entire equation. That's the reason that I put parentheses around here, to emphasize that the whole thing is being multiplied by 24. I mean every single term. First term is going to get multiplied by 24. Second term is also going to get multiplied by 24. And even in the back, it's going to get multiplied by 24. Every single term. The beauty of doing this is that it allows us to clear the fractions, because what do you do when you multiply fractions? Exactly right, gang symbol. I'm going to cancel on those diagonals. So what happens here is, when I go to cancel on the diagonals, I'm going to look at this diagonal right here, and I'm going to say 6 goes into 6 once, 6 goes into 24 4 times, and what am I left with right here? Yeah, just a 4x. I'm going to do the same thing right here, and I'm going to check that diagonal. What will go into both 8 and a 24? An 8. So 8 goes into 8 once, into 24 3 times. What am I left with? Yeah, just a 3x. And then here in the back, don't forget, 1 times 24 is just a 24. The beauty is the fractions are gone, completely wiped out. So now I have a very simple equation to solve, and I know that a 4x and a 3x is just a 7x. That kicks me back to what I had before, right here. 7x equals 24. So I'm going to do the very same thing, and I'm going to divide through by 7, and that's going to tell me that my x is a 24 over 7. And once again, like before, if you can simplify the fraction, do. This one won't. So like I said, the great thing about this method is it wipes out all the fractions. It uses the LCD, but uses it in a different way, because to get the LCD, you look at these two numbers, the 6 and the 8, and you say, what number will both of these go into? by saying what will they go into, that's the idea of creating this little setup right here where they're going to go into these and they're going to cancel out the fractions completely. So that means in method 2, what happens, the steps for method 2 are, get a pen to work. I'm going to multiply, here's the key, every single term, every term by that LCD, the least common denominator, to get rid of the fractions. And then you're going to solve the resulting equation, which ought to be fairly easy to do. That's method 2. Now, like I said, you decide which method you like and you go with that method. You don't have to know both. Me, I'm a big, huge fan of this second method right here because I love to wipe out those fractions. But remember, I told you that one of these methods you won't be able to use later. This is the method you won't be able to use. It is because later when you have rational expressions, you will not have that equal sign that's right here. What you're allowed to do what you're doing right here, because this is the idea of the pan balance, and you're keeping everything in balance when you multiply everything by that 24. When you're multiplying this side by 24 and this side by 24, that means you're doing it on both sides of that pan balance and you're keeping everything balanced. But when the equal sign is gone and this is no longer here, and you don't have any of this part, then what happens is you are taking this entire piece here and multiplying that by 24, and you are now changing value. Remember we said back here that 4 over 4 was just a 1, and multiplication by 1 does not change value. So this one will be okay to do later because multiplication by 1 doesn't change value. But this one won't be able to use later because multiplication by 24, that will change value. So method 2 is the one you got to be careful about. And if you are one of those people who says, I can use it now and I can't use it later and I'm going to get confused, then you need to pretend like this second method back here doesn't even exist. If you're one who will get confused later, you need to stick to method 1 if that's you. But both methods are perfectly fine. Both methods work great for now, as long as you have an equation. So that's what happens when you have equations with fractions. Let's try one more. Make sure we're good and solid on this. And I'll do both methods again just to make sure that we feel comfortable with it. So I have an x plus 3 over 3x plus a 3x over 4 equal to a 2. And I'm going to do first method 1. And recall, method 1 says I'm going to retain the idea that I have fractions here. And by doing that, I'm just going to create common denominators and add across. For a 3 and a 4, common denominator is going to be a 12. So I'm going to adjust all these to 12ths. And that means I need to take this 3 and multiply it by 4. Same thing on the numerator. So this becomes a 4x. I'm going to take the 4 and multiply it by 3. Same thing on the numerator. Again, so that I don't change value, only looks. My new numerator becomes 9x. Now, this 2, it's a 2 over 1. I multiply that 1 by 12 to create a 12. I multiply the numerator by 12. So I have a 24 over 12. So I've gotten the common denominators. I've adjusted all the numerators. Next step is to simply combine up the fractions, because that's what you do once you get common denominators. You can add the numerators. 4x and 9x is a 13x. Keep the denominator. You worked really hard to get it, so keep it. And the other side stays the same. So now, like we said before, we have a proportion, and it says that both sides are equal. If both sides are equal and the denominators are the same, as you can see right here, then what does that mean about those numerators? The numerators have got to be the same. That's the only way that those two fractions can be equal to each other, if the denominators are the same. Only if those numerators are the same. So that creates a very easy equation to solve, and at this point I'm just going to divide through by 13. And that gives me x equals 24 over 13. And like we said before, if it'll simplify, do. Is there a number that'll go into both 24 and 13? Nope. So leave it alone. You don't have to turn it into a mixed number. So there's method 1. And now with method 2, with method 2, remember, I'm going to continue to use the LCD. I'm just going to use it in a different manner. So I'm going to take the entire equation, multiply absolutely all of it by 12. So I'm going to take the first term and multiply it by 12. I'm going to take the next term and multiply it by 12. And I'm going to take the last term and multiply it by 12. And remember, what happens is when I multiply fractions, I cancel in the diagonals. So here I look at the 12 and the 3 and I say what will go into both. 3 goes into 3 once, into 12 4 times. I'm left with a 4x. I look at this diagonal and I say what will go into 12 and 4. 4 will. 4 goes into 4 once, into 12 3 times. I'm left with a 9x. And then in the back, 2 times 12 is 24. Once again, pretty easy equation to solve because 4x and 9x is a 13x. And now all I have to do is divide by 13. And so that tells me that my x is a 24 over 13, which is the exact same thing that I got before. And so yet again, I know that it's not going to reduce, not simplify. So this is how you solve linear equations that have fractions in them. And like I said before, you decide which method you like, you go with that method. You don't necessarily have to know both of them. So now we're going to take a look at equations where we have to satisfy certain conditions. Okay. To satisfy certain conditions. And let's take an example here. So I'm going to find all values of x that satisfy the given conditions. And those conditions are going to be this. My y sub 1 is going to equal 7 times 3x minus 2 plus 5. And my y sub 2 is going to equal 6 times 2x, whoops, minus 1, not plus 1, excuse me, minus 1 plus 24. And I want my y sub 1 to equal my y sub 2. So what happens in this situation is, don't let the subscripts confuse you, because the sub 1 simply means this is the first y and this is the second y. That's all it is. I'm not sure why they decided not to use a y and a z. I don't know. But we've got a y sub 1 and a y sub 2. So here's the condition. I want those two to be equal to each other. Well, if y sub 1 is all of this, and that means I should be able to take all that and put it right here. If y sub 2 is all of this, that means I should be able to take all that and put it right there. And when I do, suddenly I create an equation that looks like this. That's the type of equation we know how to solve. We've done this before. We know that we need to take, here's the wall that we've talked about, right through here. And we know that we need to take this side and simplify the side and create just simply a variable and a constant. And then we need to do the same thing on the other side and simplify this side and create just a variable and a constant. And once we've got that, we can start shifting things across that wall. So for right now, what I'm going to do is just simply simplify. And we know that when we simplify, we are going to distribute. So we're going to take that 7 and distribute it through the parentheses. So 7 times 3x is going to be a 21x. 7 times negative 2 is a negative 14. But that's not as simple as that will get. So I need to combine up my negative 14 and my 5. Negative 14 and 5 will be a negative 9. Now that side is as simple as it will get. So I'm going to try to simplify the other side, and I'm going to distribute the 6 through. 6 times 2x is going to be a 12x. 6 times negative 1 is a negative 6. But that side is not as simple as it will get because I can combine up the negative 6 and the 24. Negative 6 and 24 will give me 18. Now that side is as simple as it will get. So at this point, I just need to separate my variables and my constants, get them on completely opposite sides, and remember it does not matter which side you get on. So what I'm going to do is I'm going to subtract that 12x from both sides. And a 21x minus a 12x, I'm running out of room, I'm going to go over here. 21x minus 12x is a 9x. And on this side, 12 minus 12 cancels out, I'm left with an 18. Now we know that we got to undo what's been done to the variable in opposite order. If we knew what the x was and plugged it in there, we would first multiply it by 9, then subtract 9. That subtracting 9 is the first thing we're going to fix. So we're going to undo that by adding 9. And that gives us a 9x equal to a 27. And now that's very easy to do. And I think we all know that at this point what we're going to do is we're going to divide through by 9. And that tells me that x is going to be a 3. And you know you can check that because if you put the 3 right in here and right in here and do all the order of operations, the left side and the right side will be the same. So that 3 is the number that will satisfy this condition right here that will create this and this to be the same. So that's how you solve equations that satisfy certain conditions. The last thing that we're going to look at to end out this section is types of equations. And I know you're probably thinking, wait a minute, we've been doing all kinds of different types of equations. We've been doing equations that look like this. We've been doing equations with fractions in them. Really and truly, we have not been doing different types of equations. All of these, believe it or not, have been the same type. So now we're going to look at the different types. So first we're going to look at, actually this isn't the first type that we're going to look at. We're going to go back and fill this in. The second type is going to be a conditional. Oops. And then the last type that we're going to look at is going to be an inconsistent. So let's go back and let's take a look at just the conditional equation. Now with the conditional equation, you know how to solve this particular example. You know that what you're going to do is you're going to distribute that 4 through the parentheses. And when you do, you're going to get a 5x minus 20 equal to a 4x minus 8. You also know that you need to combine up your like terms, and you're going to move all the x's to one side, variables to the other side. So I'm going to subtract the 4x. And that will give me x minus 20 equal to a negative 8. Don't forget the name tag. That is a negative 8. Name tag, sign in front, sign that goes. Now what I'm going to do is I'm going to add a 20 to the other side. And so that will give me x equal to 12. So we have found the solution. So a conditional equation is the type of equation that is not true for all real numbers, but is true for, erase here, is true for at least one real number. Number, not numbers. So in other words, with a conditional equation, I know that I'm going to have at least one solution. I might have two solutions, I might have three solutions, but without a doubt, I know that I'm definitely going to have at least one solution. The other thing to note about a conditional equation is how to express the solution set. Now remember, you are looking for a set of numbers that you can plug back in here for the x and get the left and the right side to be equal to each other, get them to be the same. You want a set of numbers. What are the numbers that will work and make that happen? So to denote that you're looking for a set, you use the braces. That is set notation. What it means is the numbers inside there are the ones that will work. In this particular case, there's only one number that will work. So I would say the set of all numbers that are just a 12. And that's how you would express your answer in this case. So in a general sense, you would just simply say x equal to whatever that number may be, or two or three numbers, whatever they are. That's how you express your solution set. Note that, I mean, most of the time we just write it this way, and this is perfectly fine. I'll accept that. It'll be great. But I want to make sure that you're aware that in my math lab, when you put your answer in there, you'll see this, and you'll see your box, but you'll see a brace around the box. My math lab is just simply trying to drive home to you that you are generating a set of numbers for your answer. And so you'll insert into the box the numbers that are included in that set. But that's what a conditional equation looks like. And that's the type we're used to seeing. We've been doing conditional equations a lot. Let's kick now to the inconsistent equation. The inconsistent equation, what happens here is when I go to solve this one, I'm trying to change my pen color here. When I go to solve this and I distribute my 5 through, I get 5x minus 20 equal to 5x minus 50. And then when I go to subtract those 5x's, I get a negative 20 equal to a negative 50. And I don't know about you, but this is the point when I have a little bit of a panic attack and go, wait a minute, all my variables can't disappear. I have to have an x equal to a particular number. I go back and I check all my work and I see, no, I did everything right. There's nothing wrong with what I did. So then I examine what's happening here. And what this statement says is that a negative 20 is a negative 50. Well, is a negative 20 a negative 50? No, they're never going to be equal. They absolutely cannot be equal. And remember, what I'm trying to do is I'm trying to figure out what numbers will work in there. Well, this is what we call a false statement. When the statement is false, what that means is there is absolutely no number that you can plug back in here and get the left and the right side to be the same. Nothing will work. You throw a number at me, we'll try it, it's not going to work. Nothing will work. So that's what we call an inconsistent equation. And the definition of an inconsistent equation is an equation that is not true for any number, for any real number. Inconsistent, and there's nothing that will work. And so if that's the case, then how many solutions do you have? You have absolutely no solutions at all. But now the question is, how do I express the fact that I have no solutions? Because remember, on the other one, we said we had a solution set, and how did we express the solution set? So we got the same idea here. What is my solution set going to look like? Well, remember, this is the set of numbers that will work, but the catch is I have no numbers that will work. So we have a set with nothing in it. That's what we call the empty set. You just have your braces and have it blank. Another option that you've got is this. This is the symbol that we call null set, also called empty set. Because it's the set that's empty. It's the set that has absolutely nothing in it. Either one of those is going to be perfectly fine. So when you go through this example here and you need to write your answer, this is how you would express your answer, empty set. Or you could write this, the empty braces. What you don't want to do, and students do this all the time, you don't want to write this, because this indicates that you definitely do have a set, and you have a set with something in it. You have a set with an empty set in it. And you know that's not the case. You have a set with absolutely nothing in it. So you either leave it as the empty set that way, or you utilize your null set. Either one's going to be just fine. Most people utilize this null set, and that's totally fine. Now, kick it back to the inconsistent equation. I'm sorry. No, that should say, I'm very sorry. That should say identity. The identity. I apologize. There we go. What happens with an identity is you go to solve it. I'm going to distribute this through. Once I distribute it through and I combine up my like terms, 5x minus 20 on this side, 5x minus 20 on this side. And then when I try to move all my variables to one side, constants on the other side, I'm going to subtract a 5x here, subtract a 5x here. I'm left with a negative 20 on this side and another negative 20 on this side. And once again, I have my panic attack because it looks like I messed up somewhere because my variables are gone. But when I go back and examine my work, I realize, no, I did everything right. There's nothing wrong at all. And we discovered on our inconsistent one that it's possible to wipe out all the variables. And what we did was we simply examined the statement in the end and said, is it true or is it false? Let's go back to this one. If we go and examine this statement, it says a negative 20 is a negative 20. Well, is a negative 20 a negative 20? Sure is, and it's always going to be. So this is a true statement. And what that tells me is any number at all that you can think of, every number I can plug in right here, and I'm going to get the left side and the right side to be the same. Every single number will work. A 20 will work, a negative 20 will work, a 0 will work, a fraction will work, a decimal will work, every single thing will work. So the identity is going to be an equation that is true for all real numbers. Absolutely every number you can think of. So if that's the case, well then how many solutions do you have? Sure, if you're talking about all of them, then you're going to have infinitely many solutions. Absolutely all of them. But like before, how do I express that? How do I put it into a solution set? Well, remember, this is a set. The set of numbers. So I'm going to say the set of all x's such that x is a real number. Set of all x's such that x is a real number. Basically what that says is all the real numbers will work. So you could write that as well. And another option is to simply write it this way. This symbol, it's a capital R with 2 bars in it. That is the symbol for all real numbers. And it means the very same thing as the other two. I believe my math lab, if I remember right, it has a multiple choice option. I think that this might be one of the options, or it might say this. I can't quite remember what it does. All three of them mean the very same thing. On the test, I'm not going to be terribly picky. I just want you to be able to express that you have all real numbers. Most people do this, Works for me, not a problem at all. You really want to impress me though. If you want to impress me, then write this. That'll be awesome. But I'm totally okay with this. The whole idea is when you come up with a true statement, like you see right here, then your answer is going to be all real numbers. When you come up with a false statement, like you see right here, then your answer is going to be null set. One other thing that I want to point out is oftentimes students will get down to, like I said, right here, and they will say, okay, I have to have a variable in there. Like, for instance, when they get to this part, the 5x minus 20 equal to the 5x minus 20. Some people don't subtract the 5x. Some people actually will add the 20 to both sides, and that's okay. When you do that, you get a 5x equal to a 5x. And then a lot of times what they'll do, instead of simply recognizing that I have a 5x over here and a 5x over here, and that makes the two the same, and you could stop right there and just call it quits and call it all real numbers. But a lot of people don't recognize that, and they keep on going, which is fine. But if you keep on going, then what happens is you get, you divide through by 5 and divide through by 5, and you get x equals x. Again, it's the same thing on both sides, so it's going to indicate all real numbers. But students panic, and so they say, well, what I'm going to do is at this point right back here, oftentimes what they'll do is they'll say, I'm going to subtract the 5x here and subtract the 5x here. Now, when you do, if you have 5x's sitting in front of you and you take 5x's out, you have nothing left. And the same thing will happen over here, because frequently students will make this the answer. They'll call this x because they think they have to have an x in there, and recognize that this is a 0, but truly this is what the answer should be, 0 equals 0. That again is a true statement, and that would indicate that your answer is going to be all real numbers, like here, as opposed to this. That is definitely not the right answer. So be very careful about that. But that is what happens with your equations that have fractions in them. That's what happens with equations that satisfy certain conditions. And that is how you handle all your different types of equations. So you've now seen everything you need to see in section 1, 2. You are good to go there, and you can take off.